Hey guys, so in this video, I'm going to be going over questions 1 through 4 from Handout 1, mostly about proteins, but there's a little bit of chem in there at the beginning. So yeah, let's go ahead and get to it. So this first question is asking you just basically like, do you know what a hydrogen bond is? Just a quick review, or if you haven't gone over it yet, not every hydrogen you see in a molecule can do hydrogen bonding. Hydrogen bonding can happen if you have a hydrogen attached to a fluorine, if you have a hydrogen attached to an oxygen, or if you have a hydrogen attached to a nitrogen. So they say hydrogen bonding is like fun stuff. So knowing that, this question's a lot easier, right? So this is an NH, that's okay, that can do hydrogen bonding, that can do hydrogen bonding. An OH group, that can do hydrogen bonding. In this carbon to hydrogen bond, don't worry about the details of this that much, just be able to recognize it. There's not a big enough difference in electronegativity for this to kind of like want to make a bond with something else here. So, oh, sorry, this is the answer, right? Because it's the incorrect example. Cool. Well, this next one, we're considering 2 amino acids, tyrosine and phenylalanine. And we want to know which amino acid will be more soluble in water. So we went over this kind of in the chem review video, like the one you watched before this, hopefully. So I'll go over this quickly, but it's going to be soluble in water if it's polar, right? Water is a polar molecule, like dissolves like. How do we know which one is polar? You want to look at, we talked about the backbone of every, wow, let me redo that. We talked about that the backbone of every amino acid is the same. Backbones of amino acids are the same, so we're not going to compare the backbones. We are interested in comparing the R groups. And when you look at the R group of phenylalanine, you see lots of carbons and hydrogens, so it's nonpolar. And when you look at the R group of tyrosine, you see like, okay, there's an OH group, that makes it a little different. That makes it polar, like dissolves like. So tyrosine will be the one that is a little bit more soluble in water. Cool. Next, we want to draw the products of a dehydration reaction. And like pretty much what you need to know about dehydration or condensation reaction is it forms water. Cool. Also, like in my first video, when I talked about study habits for bio, drawing stuff out is a really good way to kind of like learn it a little bit better. Like you're getting a little bit more active learning, getting a little bit more in depth. So this is something you should be doing. So instead of NH2, I'm going to redraw it like this, H and H. That'll make this easier to see. So we want to form water. So you're looking for where you can find kind of like a little OH, or sorry, H2 and O. Here we see an oxygen and a hydrogen. Let's get that second hydrogen here. And then we form water. Cool. So this is kind of something that might help you later, but anytime you see an OH group, which is an alcohol, you're only one hydrogen away from making that water and doing that dehydration reaction. So anytime you see an OH group, that means you can add something there. Like you can add another amino acid there or add another monomer there. So like think what you can add to the alcohol. Anytime you see an OH group, you can do a dehydration reaction there, right? A. Cool. So when you, let me just erase this. So where you take the OH and the H from, that goes away. So hopefully this is working. So where that was, you now have a new bond. So you now have a brand new bond here, right? Getting rid of that H2O from water, and now we have a brand new bond here. Let's go ahead and kind of redraw that. What is that new bond between? It's between the C double bonded O, and it's between the NH. Remember that the two functional groups, it's between the amine and the carboxylic acid. Now we can redraw everything else here. There's a CH, then there's a COH, then there's the R group. I'm not gonna redraw the R group. Cool, and then on here, there's another CH, H2, and then there is the R group of the tyrosine. Cool, so now that we have that down, let's go ahead and label the peptide bond. The peptide bonds is a covalent bond. So a covalent bond is the strongest bond type. So it's the strongest bond. It's gonna tie those two atoms together really strongly. And it's anytime you see like a normal bond drawn. So when you see lines like this, that's letting you know it's a covalent bond. It's the bonds you're used to seeing. So a peptide bond is a type of covalent bond. So covalent bonds are the umbrella term. Peptide bonds are just a type of it. The peptide bond is the new bond. So can you pause this video and on this, kind of pick out where the new bond is that you made? Okay, so hopefully you're remembering, oh, it's between the carboxylic acid of one and the amine of the other. It's this new bond here. So this is the peptide bond. Then every protein has a C terminus and an N terminus, where the terminus is the end terminus is the end with the amine. This is the end terminus, and the C terminus is the end with the carboxylic acid C terminus. So this will be really important because we're going to keep learning about proteins, especially when we get to translation, like how you make proteins. Knowing what the N terminus and the C terminus means is going to be important. Cool, so I'm gonna erase everything except for this drawing here because that's gonna be really helpful for this next question that we do. Okay, cool. So proteins, you went over in lecture, have different levels, like the primary, secondary, tertiary, and quaternary levels, and you need to know what's going on at each of these levels. So let's take this one at a time. What forces hold the protein together at these different levels? So the primary level of a protein is just the order of amino acids, or AAs. And take a second and reflect based off what we just did. What is holding together amino acids? Right, we just drew two amino acids being linked together by this peptide bond. So that's what's holding together those amino acids. So the forces holding the protein together at the primary level are just the peptide bonds. Which are a type of strong covalent bonds. So I'm going to put that in there, covalent. I'm hoping that as you watch these videos over the quarter, my handwriting improves on this. Hopefully you see that. Cool, so that's the primary level. It's just simply the order of amino acids and just the peptide bonds that hold them together. Next, we have the secondary level of protein structure. So that is just alpha helixes, the structure alpha helix, and beta sheets. So what are the forces holding alpha helixes and beta sheets together, like the things that kind of look like this? Don't worry about the details of this, they're blurry. The main point is almost every single protein can do these. So if all the proteins can do these, it must be something that every protein like has the same of, right? What do amino acids always have the same of? Hopefully you're thinking about the backbone, right? The backbone of the amino acids are all the same. So that means every protein that's made of amino acids is going to have the same backbone. So the alpha helixes and beta sheets are all about the backbone. And what types of bonds are happening here? You can kind of tell it's like, maybe not, it's a little blurry, but it's all about hydrogen bonding. In the backbone of the amino acids. So it's all about those NH groups and the C double bonded to O groups of the N terminus and the C terminus of different amino acids. Cool. Next we can talk about, oh, and by the way, hydrogen bonding. Do you guys think it's going to be stronger or weaker than covalent bonding? Okay, hopefully you remember that I just said that covalent bonds are the strongest bonds. Everything besides a covalent bond, we're just going to consider like a weak force. So hydrogen bondings, even though they're like strong compared to other things, in bio just consider them a weak force. The only strong force is covalent bonds. Next we have the tertiary level of protein structure. This is all about the different R group interactions. Cool. So let's think about the different R groups that we have. Like we have so many different R groups, which means we have so many different types of interactions. So we're gonna have a pretty like big variety of stuff going on here. Okay, sorry, I had to pause the video there real quick. So yeah, we have tertiary level is all about R group interactions, and we have lots of different R groups. So we're gonna have lots of different interactions. So some of the things we're gonna have, we basically have like every single bond type here. So there's gonna be hydrogen bonding between the R groups. You're also gonna have hydrophobic interactions. So that's what I explained in the last video. Hydrophobic things will kind of clump together. Just like hydrophobic R groups will kind of want to clump together in a protein. We also have ionic interactions. That's whenever you see like ions, right, or like charges being attracted to each other. You can also have disulfide bridges. These bridges are actually the only type of covalent bond. Oops. They are, yeah, the covalent bonds. The only type of covalent bond at the tertiary level. And it's only the amino acid cysteine that can do this. So cysteine can make disulfide bridges. Okay, cool. Yeah, so at the tertiary level, really like all types of interactions are possible. Let's go ahead and talk about the quaternary level of proteins. So at the quaternary level, this is all about like different proteins being attached to each other. So this is all about interactions between two or more proteins. So sometimes like a big protein is actually made of a bunch of smaller ones. As soon as you start talking about more than one protein being attached to each other, now you're talking about a protein that has quaternary structure. And this is going to have all the same forces as tertiary. It's going to have hydrogen bonding. Let me write that higher up here. It's going to have all of them. So it's going to have hydrogen bonding. It's going to have hydrophobic interactions. It's going to have ionic interactions whenever you see a charge. It's also going to have disulfide bridges. Cool. So let's go ahead and move on to the next question. So let's say we heat up a protein and heat's going to disrupt. Let me correct this a little bit. Heat disrupts the weaker bonds. The weaker bonds that hold the protein together. So what level of protein structure will be completely unaffected? So now that we've gone over this, give yourself a second and pause the video and see if you can answer this question. Okay, welcome back. So the thing that will be unaffected are the strong bonds, or the strong covalent bonds. So this would be the peptide bonds, right? The things that are linking together the amino acid. The disulfide bridges would be safe. So that would show up in tertiary and quaternary structure. So which level would be completely unaffected? So this means that like, so which level would be completely unaffected? That would just be the primary level, right? The primary level only has these strong covalent bonds. So this would be completely unaffected. At the secondary level, if you heated it up, all the hydrogen bonds, they would get denatured. At the tertiary level, hydrogen bonds, ionic bonds, hydrophobic interactions, those would be denatured. You'd still have these disulfide bridges, but like everything else would basically be ruined. So yeah, when you heat up a protein, to a certain extent, all the covalent bonds, they're gonna last a little bit longer because they're a little bit stronger. Cool. Yeah, and that is it for that video. Feel free to email me if you need any clarifications on this. Other than that, I will see you in the next vid.